Connectedness was defined quite abstractly in terms of closed and open sets. Path connectedness is a more concrete or tangible version of it. It is asking whether given any 2 points in a space X, there's actually a path connecting these, which we will define in a moment. But this picture is a bit misleading, won't matter in this course, but when you come to algebraic topology or something, the path is allowed to cross itself. So let's take X as a topological space. And a path in X is just a continuous map from the interval alpha from 0, 1 to X. Okay. It's convenient to always use a fixed domain. You could use any other closed intervals. And we say, in this case, alpha is a path. It has a beginning from alpha of 0 to alpha of 1. And the space is path connected. X is path connected. Implies, it's not implies, it's a definition. If for all points, let's say a, b in X, there exists a path alpha mapping 0, 1 to X from A to B, which I might as well write out explicitly such that alpha of 0 is A and alpha of 1 is B. So if there's a path from A to B, we say the space is path connected. Okay, and the first thing to note here is an easy result, which is that if X is path connected, then it is indeed connected. So this is a strict refinement of being connected. In the next segment, we'll see the converse is not true, but first we'll prove this, and then we'll look at path connectivity in its own right. Okay, so path connectivity may be a better term than connectedness, but I'll stick to this one, which is commonly used. So if X is path connected, then X is connected. Well, we claim, so remember that a space is connected if any 2 points are in the same connected set. Okay, so if AB belong to X and alpha is a path from A to B, by which I mean path in X from A to B, okay, then what we know is the image of a connected set is connected. So the alpha of 0, 1 contained in X is a connected set. Containing A and B. So this implies A and B are in the same connected component. So we showed that there's a decomposition into connected component, and this is true for all AB in X. That means there's only one connected component, which implies that X is connected. X itself has to be connected, otherwise there is more than one connected component. So one of the things that makes path connectedness useful, path connectivity useful, is we can decompose into path components just as we could decompose into components, connected components, and the way in which we can do it is to use the fact that path connectivity. I should make a definition before saying this. We define a relation which is going to turn out to be being in the same path component on points in X. So it's on X itself as a set, points in X, by, let's just say, A is related to B if and only if there exists a path alpha from A to B in X. So it's a path A. And here's the following main theorem. I'm calling it a theorem because it's actually, the result is nice, but its proof is even more important. Indeed, you'd start algebraic topology with the proof, because this involves path operations. Though here we won't frame it as that, it is also quite a elementary thing, and we'll look at it in a more elementary way. Theorem tilde is an equivalence relation. Okay, so some pictures here, but first case, well, we have to show two things. Reflexive, that is A is equivalent to A. Okay, so path from A to A, well, just stay still, is alpha of S is 1 for all S. Sorry, not 1, it's the point A. S and 0, 1. Okay. Symmetric. This is so this is kind of like an identity. It's just a constant path. So suppose AB belongs to X, and alpha and A is equivalent to B. Then there exists alpha mapping 0, 1 to X, such that alpha is from A to B. We can spell that out as alpha of 0 is A and alpha of 1 is B. So now a path from B to A in X is given by, just reverse your time. Start at 1, go backwards to 0. So it's alpha bar of S. So let me, to be explicit, say what the domain and codomain is. It's also mapped 0, 1 to X. It has to, because it's a path. Alpha bar of X is alpha of 1 minus S. Okay, and this is a composition of continuous functions, so it's continuous, and it starts at A, B, and ends at A. Okay, and finally, the thing that takes more work but is interesting is transitivity. I have 3 points now, A, B, and C. Now, to avoid misleading, though it won't matter in this course, as I said, I will have a path from A to B and a path from B to C. Now, the path from B to C could intersect the path from A to B, and they may intersect themselves also. We have now assumptions about them being disjoint from each other. But you have this path, and you can see a path from A to B, from A to C, by composing these two in a sense, by taking one followed by the other. So the path we generate is, well, let's first set up the hypothesis. So suppose we have A, B, C in X, and A is equivalent to B and B is equivalent to C. Then we have, let alpha, beta be paths from A to B and B to C respectively. Now what we have to do is go at double speed from A to B and then go from B to C. So one can see that that is given by the following. Then a path from A to C is given by alpha star beta. So I should call it alpha. Let me write it in domain and codomain 0, 1 to X by alpha star beta of S at the point S is going to be okay. So one has to check a little thing with care. Is going to be equal to alpha of 2S. 0 is less than or equal to S is less than or equal to half, and beta of 2S minus 1 if half is less than or equal to S is less than or equal to 1. Okay, and so since I have the formula here, well, this is well defined. Why is this well defined? As well, there's only one overlapping point, half, as alpha of 2 into half is alpha of 1, which is B, and beta of 2 into half minus 1 is going to be beta of 0, which is also b. So this formula is actually well defined, and now once you know it's well defined, it is continuous by the pasting lemma. Namely, we have functions that are continuous on the two intervals 0, half and half 1. Okay, so this I'm just simply circling the overlapping point. On these two intervals, they are compositions of continuous functions, so they are continuous. Alpha, beta are assumed to be continuous, and linear functions are continuous because continuity coincides with real function continuity in those cases. Indeed, we showed explicitly such functions are continuous. Okay, so these are continuous functions on sets. They agree, so they give you a global function. These are both closed sets, but we have only finitely many, in fact 2 of them. And hence since these two glue together to give a continuous function. The crucial point is that the first path ended where the second began. Otherwise, this formula will not be well defined if I write it like this. And if I change one of these to less than to make it well defined, it won't be continuous. Okay, so let me just make a comment here. So just here, no need to go to a new page for this. Hence gives a partition. So when we have an equivalence relation, you automatically get a partition into path connected components or path components. Or path connected components, whatever term one prefers. So as soon as you have an equivalence relation, you get a decomposition, and two objects are related, in this case, which means a path joining them, if and only if they are in the same class. Okay, and we have seen that any of these path components being path connected is connected. Okay, the next segment will show that the converse is not true. It's not so important in set topology, except this is a very good illustration of working with the definitions and so on. And this is very important when one gets to algebraic topology anyway.